Okay, hi everyone. And first of all, thank you very much for the invitation for being here and talk about short baseline liquid argon experiments. Do we have a point of sticker or should I use this? It works, okay, good. So it's a pleasure, of course, to be at a conference in person and see some faces. So thank you again for organizing all of this. So my presentation will be focused, first of all, on a few words on motivation for short baseline neutrino experiment. I will talk about the picture of beyond three neutrino mixing and alternative physics scenario, and I will emphasize in particular this part. I will try to motivate why liquid argon time projection chamber are very good detectors for this type of physics. And I will go through first result recently released by the microboon experiment. I will touch a little bit on the some results from the Argonaut experiment, and then I will focus on the short baseline neutrino program, all those experiments at Fermilab. I will not go into explain what we normally call these neutrino anomalies. We have accelerator anomalies from LSND and mini-boom experiment, plus reactor and gallium anomalies. All of these could be pointing at BSM physics in the neutrino sector that could lead to the existence of additional sterile neutrino state at large delta M square, driving a neutrino oscillation at small distance. So the big question is there something beyond the three neutrino mixing? There are, so short baseline neutrino experiments are mainly motivated by these anomalies, anomalous electron flavor appearance and disappearance that may indicate new neutrinos participating in the oscillation, but also they are wonderful, as we have seen also from previous speaker, to make measurement of, I would prefer to call maybe neutrino interaction more than neutrino cross-section more in general, which are important per se, plus are important for understanding interaction, informing neutrino oscillation measurement. But as we probably all know nowadays, it is a very evolving landscape. So we started with these anomalies, but there are several alternative potential explanations from more recently emerging new physics scenarios from theory. And we are, for example, we are having a lot of meetings with theorists. And here, for example, you can see from some colleagues a blackboard, which is the theory version of an experiment I will talk about, which is the SPND experiment, just to say that there is a lot to measure in the landscape of this potential explanation. So the parameter space of new oscillation continues to be new interaction can continue to be explored with accelerator-based, which are including decay in flight and decay at rest experiment, and reactor-based experiment. And we will have a presentation on the review of the reactor experiment at this conference on Wednesday. Here, I will focus on some of the recent results from accelerator-based decay in flight, like liquid argon TPC experiment. And as I said, I will talk about the short baseline neutrino program, and also I will touch on the Argonaut experiment at Fermilab. So a few words of why doing BSM physics in short baseline liquid argon TPC experiment is a good and important piece of physics. So the combination of high intensity proton beam, which means high intensity neutrino beam produced by proton interaction in the target, pion and kaon decay in flight, coupled with large mass detectors close to the beam target, which in the case of the liquid argon have very good event imaging, granularity for calorimetry and particle identification, good timing resolution, and also low energy threshold, as I will show in a few slides, open up the possibility of several opportunities to probe new signature for new physics scenario in the neutrino sector, which means modification to the, our understanding of the neutrino oscillation picture, and at the same time look beyond that. So in case, novel experimental signatures are produced by the interaction of proton in the target. So why liquid argon time projection chamber? The technology, here you can see an historical bubble chamber event. Here you can see a neutrino event. The neutrino interact here, produce a proton, a muon, and a pion. The same way in this event, a proton, a pion, and a muon is produced. And you can see by eye that liquid argon data has bubble chamber quality, with the plus of having the possibility to do energy measurement, calorimetry. So liquid argon is the technology of choice, as we know, for precision physics. Few words about what we can do in liquid argon, because I think it's important in the context of the message that I would like to give today. So the liquid argon TPC can measure neutrino interaction with very good position resolution, has capability to measure energy deposition from some ABB to few GeV level. And how it works very quickly, we go from raw data, from the signal of the wires, and then produce these images in which normally there is the drift time on one axis and the wire number on the other axis. And then we reconstruct heats, we cluster the heats, and then doing this on different multiple 2D projection, we go to a 3D reconstruction where we reconstruct tracks and shower. So excellent imaging capability. From the total charge deposited, we can calculate, we can have a measurement of the deposited energy, so we do calorimetry. And by doing the energy deposition along the track, we can do particle identification. So we can recognize different types of particles. Plus, modern detectors have also very sophisticated light detection system, as I will show you some example. So they are very good at a few nanosecond level timing resolution. I cannot resist from showing a certain number of events, just to give you the feeling. Those are for the Argonaut experiment, but you will see in the following slide beautiful events also from the microboon experiment that give you the idea that what you see by eye is something that can go from easy topology, like here you have just a muon or just an electron, and you can see by eye if there is hadronic activity at the vertex or not. So it's a matter of developing as sophisticated as possible reconstruction technique and disentangle the existence of all of this in your events. Then you can go to more complicated topology, like having, I don't know, a proton and a muon, like here, two protons, a proton and a kaon, the same for the electron side, to more crowded events, the deep and elastic scattering events in which you see a lot of different tracks, or events like the one here, where by eye you can clearly see that in these events there are 2 pi zeros that produce 4 gamma showers. So the other important characteristics of the liquid argon TPC is the capability to recognize electrons from photons. We all know this plot is so famous that I show it, but I'm sure all of us know very well. The mini-boon excess, so data and all the different components from Monte Carlo prediction. There is this famous electron-like excess, this low energy excess. But in a Cherenkov detector, as you can see, the major background is coming from events where a pi zero or a gamma is indistinguishable from an electron. And so there is a big component of background coming from that. In liquid argon TPC, there are 2 ways in which we recognize electron from gammas. The first one is that we can see, again, the imaging capability and do our reconstruction as better as possible to recognize that in case of an electron, that the neutrino interaction is here, there is no gap from the vertex, while in the case of gammas, there is a gap from the vertex. The other is to study the energy deposition per unit track length at the beginning of the track before the shower start to develop, and look and recognize an electron that deposit around 2 MeV per centimeter in liquid argon from gammas, in which when the pair produce, there is an electron and the positron, so the ionization is basically double. And this is an important discrimination that allow us to, for example, look better the microboon. This is where the microboon experiment was born, in order to test the microboon, the mini boon excess this way. Quickly, another characteristic of the liquid argon is that liquid argon TPC have relatively recent demonstrated to be able to detect and reconstruct sub-MeV energy deposition. So this is an analysis that done by the Argonaut experiment, in which we have been able to reach an energy threshold of 300 keV, and we have been able to reconstruct. So this is a neutrino interaction where you see a proton and a muon, and there are some what we can call blips around the neutrino interaction. And we have been able to reconstruct, develop specific reconstruction algorithm to reconstruct those blips. And they have been identified as electrons produced by Compton scattering of the excitation photons from the nucleus, and photon produced by neutron inelastic interaction. This capability is very important. And, you know, for example, one important point is that they could be added to the energy in the reconstruction of the neutrino energy. And as has been demonstrated by Alex, a collaborator, this can have a big impact in the neutrino energy reconstruction. And it's a capability that we are trying to study and include in our reconstruction. Of course, this is important to reconstruct neutrino interaction at very low energy, like supernova events. And as I will show you at the end of my presentation, was also used to do some BSM geophysics scenario studies in Argonaut. So I told you I was talking about all the liquid argon TPC experiment I'm talking about are at Fermilab. So just a quick recap about the neutrino beam that are available at Fermilab. There is the NUMI beam you heard about, average energy between 4 and 7 GeV and is tunable. And instead, there is the booster neutrino beam produced by the booster, so 8 GeV protons in this case, while the other one is 120 GeV protons that produce a neutrino beam of an energy of about 800 MeV. So liquid argon short baseline liquid argon TPC detector at Fermilab. The first one was the Argonaut experiment, which is a tabletop size experiment, like 1 meter by 50 centimeter, which was 240 kilogram active liquid argon TPC put underground just in front of the MINOS near detector. And that was used for Argonaut measurement as a spectrometer. And the average energy was the NUMI in the low energy configuration, so around 4 GeV. The second, a much bigger detector that has been installed in Fermilab is the microboon detector, which is the world's longest running TPC at the moment. That was taking data for 5 years and concluded the physics run last year, which was put on axis on the booster beam, but is in a position in which, since the NUMI and the booster beam, they cross each other, a microboon can also see off-axis neutrinos from NUMI. The story of the booster beam will be completed when other two detectors, the short baseline near detector, SPND, will be added as near detector, and the Icarus detector as far detector. Also Icarus as microboon will see neutrinos from both the booster and NUMI off axis. So this is the short baseline program. So a near detector is will be 112 tons of liquid argon put at 110 meters, microboon 90 tons at 470 meters, and Icarus 475 tons at 600 meters. All the program has been designed at the beginning as sterile neutrino search. So using the idea is that the detectors share the same neutrino beam, the same nuclear target, the same detector technology, all this in the attempt to reduce the systematics as much as possible. As I said, microboon experiment has taken data for 5 years, has completed the physics run, and was designed to investigate the low energy excess observed by mini-boon. So the key idea here is to use the liquid argon in order to disentangle, to do a more sophisticated job in recognizing electron from photons. And the first results on what, this low energy excess have been recently released by microboon, with half of the entire statistics of data. And microboon and these results are presented basically in two categories. One is a single photon analysis. The other is analysis of, looking for a new excess. The single photon analysis, I will try to do my best. There is a lot which is going on here, but the single photon analysis basically was based to the search for neutral current delta resonance decay events, and events that have been analyzed are of those two types. So very nice event in which there is a gamma and a proton, or events where there is only one gamma. So one gamma 1p, one gamma 0p events. And those are the results in which the data here are compared with predictions from Gini expectation. And what we can see that there is no evidence for an enhanced rate of single photons from this decay above nominal Gini expectations. In order to explain the mini-boon as due to this process, the mini-boon excess, the results should be here, while we see that there is the data are instead, they show no evidence of a big excess in this specific channel. The other big part of the analysis done by microboon, which was three independent reconstruction framework have been used, and basically the results are presented in 4 different channels. Those two use the same reconstruction technology, and they look basically, we heard a lot about this, so I don't need to repeat what I mean. CC 0 pion events. This is for CC 0 pion 0 proton, and here you can see a very nice candidate of this type of events. Here we have CC 0 pion with at least one proton in the final state. So like this, for example, where there are a nice electromagnetic showers, 2 proton. Another completely different analysis based on a different reconstruction framework, which is instead target to extract from the sample events which are more CCQE-like. The analysis is concentrated on 1 electron, 1 proton final state, plus there are some kinematical cuts in order to extract a sample of this type. And last but not least, this is the analysis in which is instead an inclusive analysis, again done with another reconstruction framework. The way in which all these analyses are done is that data are compared with Gini predictions, which are, the sum of the Monte Carlo prediction you can see in different colors in this plot. And in this plot, you can see what would be expected for each of the individual analyses if the the mini-boon excess was completely attributed to new events. Here there is a summary for the 4 analyses in which there is a plot of the ratio between observed and predicted rates. One is at the Gini prediction, and there are the 4 analyses with the data. The red represents what would be expected, as I said, in case of the low energy excess being exactly and all due to new events. The observed new candidate events are in agreement or below, except one case with the predicted rate from Gini. And the conclusion from this paper, in which there is a summary of the analysis, and is that the microboom can reject the hypothesis that new ECC interactions are fully responsible for the mini-boom excess at more than 97% confidence level in all the analysis. Microboom is now currently planning for the next phase of the analysis, and also that at least some of them, I guess, will include the total data sample. As I said, this is all coming from half of the data sample. Now, a few words about the status of the far detector and the near detector. The far detector is the Icarus detector. Here you can see images of the detector during the installation. This is the top of the detector, and this is the beautiful inside the detector with the cathode in the middle and 2 wire planes on each side for each of the for one of the 2 modules. The detector is actually operational. It's was taking neutrino data on, of course, booster and NUMI since October last year. And here you can see, the appearance of the booster beam and the NUMI beam. And here there are 2 events, one which is a new mu interaction from the booster, and the other which is a new interaction candidate from NUMI. The detector is actually completed, but some part of the detector are still under commissioning. The SPN detectors, since they live on surface, they are all surrounded by cosmic ray tagger, and the commissioning of the full cosmic ray tagger is actually ongoing for Icarus. Also, the Icarus detector will have on top an overburden 3-meter thick of concrete in order to make a further shielding from the cosmics. And this is under installation. We start the installation next month. The near detector instead, as I said, 112 tons of liquid argon, volume of liquid argon. The TPC assembly of the detector is almost complete. Here you can see, the TPC, this is the cathode, this is the wire plane, and this is the cathode and the wire plane from the other side. The field cage installation is almost complete. We still have to finish this part, which is left, because we still need to enter the detector, for example, to remove, here you see these black panels. It's not how the cathode will look like, but we have sensitive part of the detector, light sensitive part, so they are covered to screen from the light, and the entire detector is actually yellow appearing because everything is inside a plastic shield, which is UV shielded. The cryostat, the warm cryostat is ready, and we are about to continue the installation of the cold cryostat, the membrane cryostat. Here you can see a detail of the photon detector system with PMTs and Arapuca. The light detection system in SPND will be a very powerful one, so we are planning to profit and exploit a lot the use of the light in the detector. Here you can see a wire plane during the installation before putting inside the detector. An important characteristic of the SPND detector is that it is a natural prism. This is due to the fact that the detector is light off axis and is close to the neutrino source. Is off axis by 70 centimeters. So if you look at the front of the detector, the mu neutrino flux appear like this. This is the center of the beam, and the amount, the rate of neutrinos decrease, of course, going off axis, as you can see here, and the spectrum, as we have seen from other detectors which are off axis, will go from the on-axis flux, which is here, to the off-axis flux. So it shrinks and goes to lower energy. And this adds a lot of physics potential to the physics of SPND. Further constraint on neutrino interaction in oscillation physics, we can slice our detector and use that in oscillation analysis. We can perform target neutrino interaction measurement. And of course, as in other detector, we see that the background, for example, the major background, which is the pi0 background, it decreases a lot going off axis. And this is very useful. So this is the sensitivity of the short baseline program in the nu appearance and nu disappearance. You have seen this a lot of time, so I will not spend time. The parameter space is covered, should be covered at 5 sigma significant by the SPN program. The important point is that the SPN program, which is kind of unique, can do measurement in nu appearance and nu disappearance at the same time, with the same system in the same detector, and that's important. Because if you have nu appearance, you need to have an equivalent, the right amount of nu disappearance in order to for this to be an oscillation. In fact, this is the important point. I was talking about nu appearance and nu disappearance as hints for the possibility of the existence of this third sterile neutrino. But when we put together appearance and disappearance, we see that there is a tension, and so this means that something is going on that we may test with the SPN program and be sure, but there could be, of course, alternative explanation. This is an evolving landscape, and several alternative explanations have been given to explain, for example, the mini-Boone excess, appearance but not nu disappearance, together with other a large number of other BSM scenarios at large. Here I listed just few of them, but what's important is if we look how the final state for the different type of scenarios appear in the detector, most of them we can summarize they are single photons or single electrons. They can be overlapping, or they can have different levels of hadronic activity. So the important point here is that the unique capability of the liquid argon is where they enter into the game. We can do a lot. As I said, we can characterize the event in final state, content, and kinematics, recognize the presence of hadronic activity. So I think we can do a lot in this field. But I want to emphasize here an important point: the collaboration between experimentalists and theorists is crucial for these searches. We cannot do anything without the theorists. Just to, to prove that liquid argon can do a lot, let me show just two examples very quickly of recent analysis done by this tabletop size experiment, which is Argonaut, just to prove the capability of the liquid argon in this type of search. This is a search for heavy neutral leptons in the liquid argon TPC. And you can see here that the small Argonaut detector has been able to put a significant increase in the parameter space exclusion region with this type of analysis, in which the capability of the liquid argon are used at most. I mentioned before the small blips deposition. With this capability, we have also been able to do another physics search with Argonaut and put a leading constraint on milli charged particles, again with this small detector. So you can imagine how much we can do when we switch to larger detector, even though, also considering that they are on a different beam with respect to Argonaut. So in SPND, we have started several studies of different, possible physics scenario, and there are several which are ongoing. So the main message that I want to give here is that the SPN experiment will explore the landscape and test not only the sterile neutrino hypothesis, but also at large many physics models. And microBoone has already done some of these analyses. They are reported here, so you can go and have a look to some of them. I have no time to describe. Just few words, and then I will conclude on the fact that, you know, I mentioned at the beginning at BSM, sorry, the short baseline is not only BSM physics, but we want to do a lot of neutrino interaction measurements. And just to put in a context, and the SPN science program include precision study of neutrino-argon cross-section. Microboon has already provided several results, and we will hear about this from David Caratelli tomorrow. The Icarus detector is collecting data from NUMI that also can provide results. And SBND actually will make the world's highest statistics on cross-section measurement by recording 2 million of interactions per year from the booster. All this is due to thanks to the proximity to the neutrino source, and SPND will be certainly able to provide precision study of neutrino-argon interaction in the sub-GeV and GeV energy range. Just to put a number, in SPND there will be 5,000 neutrino events per day. This corresponds to the more or less half of the entire statistics collected by Argonaut. And just to put in numbers, in 3 months, SBND will collect as much data as Microboon has collected in the entire run. So we can really, you will see tomorrow, a lot has been done with Microboon. So you can imagine how much we can do with SPND. And here there are distribution of, so we can do inclusive and exclusive measurement of different final state. We can measure nuclear effect and also measure rate process. And as I said before, with these characteristics of being able to sample different off-axis angles in SPND, we will be able to do have many different measurements that we can use to really constrain the story here. Just a comment also on this topic. I think what we need is what I wrote here. So we will have a generational advance in terms of statistics, but I think we know we also need, as a community, experimentalists and theory together, also to try to find a way to do exactly what was said before. Alex was mentioning we need to try to find ways in which our current generator or theory models, which are not necessarily the same, fail in some place and start, you know, making change in different parts of the theory and better describe our data. So let me conclude. The liquid argon TPC detector are beautiful tools, I think. Just the example of Argonaut, I think, provide an example of how much we can do with the liquid argon TPC detector. Microboon has completed a long, huge amount of work in the first search of low energy excess. The SBN detector will perform this world-leading search in electron volt sterile neutrino, but beyond the oscillation search, there is a lot of much larger science goal, which address alternative explanation of the short baseline anomaly and other BSM exploration, and this precision study of neutrino-argon interaction, which are critical because they are important for the oscillation, but they are also important for any BSM search for which neutrino interaction are our background. Okay. Sorry for being a little bit longer, but.
Do we have questions or comments?
So what's the key issue in discriminating, is it energy resolution or whatever, in discriminating these various other channels, dark sector channels, right-handed disease, et cetera, in the non-neutrino oscillation explanations for the mini boon excess?
That's a more, a really good and general question. Of course, depends on the model you're looking at and what's the specific. I was not going in all these details, but depends on the topology of the events and depends, of course, a lot on the kinematics of those events and how much those events, the kinematic of those events, for example, is different from the kinematics of analogous signature from neutrino interaction. For example, since most of those events end up giving you, I don't know, E plus E minus pairs, for example, for those, the main background are pi zeros, of course, in which you don't recognize or you lose for any reason one of the two gammas, for example. And sometimes pi zeros at this energy are kind of asymmetric. So one of the two showers can be low energy. So this is all the work that we need to do in order to account for that. And of course, a lot depends on what the kinematics of this pair is, which of course is different depending from the origin where they are coming from. So I think even answer is complicated because it depends a lot on the model. So this is why you need to do, you know, model-specific studies.
Okay, so there's a couple more questions.
I might just be misremembering, but my impression was that the SBM program will only run in neutrino enhanced mode.
At the moment, what is approved is the neutrino run, yes.
Okay, so.
But we are talking about the possibility to run in antineutrino mode.
Okay.
But for that, my personal opinion is that you need improvements.
Yeah, I was
on
going
the
to ask,
detector side.
because it kind of makes sense if all you care about is, you know, 3+1 steriles to only run in one mode. But I mean, my sort of naive guess is you would gain a lot when you're trying to differentiate between all these additional searches. Okay, so that's something that's on.
Yeah, it's something which, you know, by the way, I should thank you for your question, because we are doing an R&D actually to understand what's the minimum field that magnetic field you would need in a liquid argon TPC in order to recognize electron from positrons. And there is some R&D ongoing in order to magnetize the liquid argon. And for example, the SPND detector has space around the current instrumented area in which, you know, some coils could be put in order to magnetize the detector. So it's my personal dream, for example, to run in antineutrino mode. So thanks for the question.
A slightly more technical question.
Yes.
But, I've read in the literature about certain concerns of changing light yield in liquid argon as a function of time. Maybe have you, from an insider's perspective, have you seen that in microboon, and to what extent is this a real issue, and how is it being addressed?
Oh, an expert on this study is sitting nearby you, so if you don't mind, I will ask David to answer this question that I know, but okay.
Sure, thanks.
Certainly do better than me.
Okay. Yeah, so in microboon, we've seen a decline in the light yield over kind of at half point through our data taking, I'd say. And it's something that on a kind of detector physics side is an interesting open question tied to, there's lots of different kind of microphysics processes that can contribute to that, whether it's absorption or quenching along the path of the photon propagation. From the point of view of the analyses, we have a time-dependent modeling of the detector, including a time-dependent light yield, which we use to replicate this in addition to detector systematic uncertainties that account for this variation. But yeah, it in and of itself is actually a very interesting question for the broader topic of modeling these detectors.
Is there any sort of calibration devices being put into the next generation liquid argon TPCs to make this detecting this effect easier? Or?
In SPND, we are putting a calibration system on the cathode with LED system to calibrate, you know, regularly the PMTs, for example, which are there. Yes.
And the sensitivities that you show for SBM, do those include such a systematic?
No. That's too sophisticated for the study that I showed there. And by the way, the sensitivity that I included here are just the official one from the proposal. We are working on them and not including the, you know, the most recent thinking because it's not yet, you know, public or.
So we have two more questions.
Okay, this is a question about the sub-MeV blip detection in Argonaut.
Yes. I don't remember where it is, but I will
Yeah,
find
you
it.
showed it in some slide, but it was a bit too fast.
Yeah, I
for
know,
me.
it was at the beginning. Yeah, I know, there was, sorry about that, but okay.
Yeah, so this particular blip, what is it from?
So those blips, when you have a neutrino interaction, the blips can come from the excitation of the argon nucleus due to the the interaction with the neutrino, or from neutron inelastic interaction. And what we have done here is reconstruct those individual hits in neutrino events and compare them with a prediction from Fluka, and we find a quite good agreement between data and Monte Carlo prediction. And if you and both components are actually very important. In the paper, for example, there is a comparison also done with Gini prediction. Now, Gini does not include the de-excitation photon from the nucleus process, or at least the version of Gini that we used at that time. Now they are working on that. And you see a quite substantial difference between, if you look in the paper, between data and Monte Carlo if you don't include these components. So they are both very, very important. We have done an attempt to separate them because, you can think, should be, that the de-excitation photon are closer to the interaction vertex, while the neutron can travel. Now, Argonaut was a small detector, so the neutrons cannot travel so long because this is 90 centimeters, so it's comparable to the hadronic interaction length in argon. But you don't have, again, there is a plot in the paper, you don't have a very good separation between the two components just based on the position compared to the vertex. So it may be difficult to disentangle them, but as we were discussing at the coffee break, we are trying to do this type of study in larger detector and see if there is something more that you can do. Now that we have a way to reconstruct those type of blips, because you need a specific reconstruction process.
Would it be feasible or useful to use argon 39 as a calibration source?
I think some people are thinking about that now, but in Dune, I think. But you could do that, but you mean for calibration?
Yes.
Or for what? Yeah, some people are thinking to use
for
that
these
in
kind
Dune.
of blips, I mean.
From the Argonaut experience, our calibration were working quite well, but of course you can try to, stress the calibration in this energy range and do something different. But I don't know the status of this project in Dune, by the way. But I know some people wanted to use that.
And one last quick question: what's the signal to noise for those blips? I mean, electronic noise.
Is a good question. So, for example, in Argonaut, which had all the electronics, we have been able to reach this threshold. Now, in more modern data, for example, Microboon did some analysis of this type, and then being able to lower the threshold, I think 100 keV or something like this. SPND, for example, Microboon, Argonaut had warm electronics. Microboon had a hybrid electronic, half part in cold, a part in warm. SBND as Protodune will have all the electronics will be all cold, so we expect to have less noise than in previous detectors. So you can also think to push this even lower. Of course, it depends on the particular situation of the different detector. So there is no one number. There are many numbers.
So just one last question.
Okay, thanks for the nice talk. Is the NUMI beam going to be on during SPND run?
Yes, but SPND is too far off axis from NUMI. Where is it? Okay, here. So Icarus and Microboon can see NUMI off axis, but SBND is like 30 degrees off axis, so you have no flux.
Or maybe from the absorber, from the chaotic case at rest.
This is something that some people wanted to study, but I don't have a real answer for you right now.
Yeah, and the other one was to clarify the prism concept here is just you're not moving the detector.
No,
right?
okay, that's the beauty of the concept. The concept is that you can sample different off-axis fluxes with the same detector. You don't move your detector because the beam, you are so close to the source that the beam is very focused.
I understand. But so is this this dependence on the angle well understood? I'm just concerned because the flux is different from what Microboon and Icarus would see from what you're saying.
Yeah, but this is, okay,
So,
I had no time to explain. But for example, this is actually, okay, first of all, the flux is not so different in SPN because they're quite close. They're not along baseline. But also, this is why where I say further constraint on neutrino interaction oscillation physics, because what you can do is to use the different fluxes in the different off-axis region of the detector and build, you know, by combination of these fluxes, exactly the same flux that you have in the near detector. And this, I cannot show the plot because it's still internal, but helps you, you know, in, you know, having better sensitivity to the oscillation quite a lot. So it's, and this is there, so we don't need to move the detector, we don't pay for it, it's for free.
great,
And,
great that it helps. Yeah.
and there's a lot of advantages. Of course, the background, which is decreasing, and that's important also, for example, for PSM physics, because your neutrino, standard neutrino flux decrease of axis. So,
Thank you.
so it's actually a very cool characteristics.
Okay, so do you want? Yes, of course. Yeah.
So I haven't heard about SBND prism before, and I just wonder how advanced the studies are because, you know, the sort of discussions on June for June prism, some severe issues for replicating the oscillated fluxes are the fact that you start on axis, right? So you know, around any sort of peak, if your oscillation is in the peak region, it's very hard to model because you end up trying to do that with a linear combination of like exponentials, which is very hard. And people have tried to get around that on June in certain ways, and I don't know how that's done. And also, by not moving the detector, it is free, but I wonder how problematic the changing efficiency is across the detector. So essentially, my question is, can you say a few words about how well studied this has been and like how advanced this is internally?
We are internally, you know, relatively advanced in this study. To be honest with you, the detector was designed like this. And to be honest, again, the main motivation why we haven't put the detector exactly on axis, the center of the detector, because we didn't want to hit the cathode. So you want to be in a sensitive region, but it turns out to be was a very good decision, actually, because you can use this characteristic. Now, the studies are quite advanced. We are using all of this, and you know, you have to keep in mind that the situation here is very different from longer baseline, because the spectrum in SPND and the spectrum at Icarus are not very different. So you can improve, but it's not that they are completely different. And this, you know, seems to work quite well. I hope we will show quite soon, but it seems to work quite well in this case. Of course, compared to the Dune near detector, I was not saying this, you don't go so far of axis, because in Dune, I think you move by moving the detector by, I don't know, 30 meters or something, you go up to maybe 3 degrees or 2-point-something degrees of axis. Here we only go to, you know, 1.8 or something of axis, but you know, it's free, so it's wonderful.
All right, so we should thank Ornella again.